Hello, hello. Welcome back to another stream. Today we'll be continuing building our compiler, and I'm pretty excited. So, what have we done last episode? Last stream, we have implemented proper error handling. So now if we write some invalid code in here like this, we have not implemented the ampersand operator yet. We do not get crash the program or get a weird output, but we rather get a nicely formatted error message like this, which just points to the location and says expected expression found bad, which is actually pretty cool, I would say. And what we have also done is we have also implemented variables. So if you all know what variables are, I suppose. Um, Now a program like this now works, and we have to remove this because e is not declared, and that's pretty cool, I would say. And we also get an error if we use an undeclared variable like e. We have some cleaning up to do. We will write some tests today to ensure that our compiler will work in the future as well. And some little bugs we also have to fix. So let's start with the bug fixing, I suppose. So the first thing that I didn't really realize last stream was that we're printing like error here and not printing the actual column and line. So that's kind of weird because if we take a look at the printer and how it's supposed to work, the idea was that we also print line and column here, and it is not printed here, and we just print error. So we'll have to take a look at that, which should be somewhere in this format error message, I suppose. Okay, we just never specify that. Okay, that's interesting. I don't even know why error is printed here. But I guess we'll have to take our column and line as parameters, and then we can just format or put this in here, something like this, I guess, where we then can say column +1 and line +1, and I guess we'll have to put that behind this. Yep, okay, and now we have to pass column and line index. And maybe it'll work now, let's see. Okay, cool. So now prints our column and our line index. And that seems correct. Okay, actually it seems wrong because we're not on line 4 here, right? I mean, maybe we are if we count that as a line break as well. So maybe if you put that like that. Okay, so it actually is correct because we just counted that as a line as well. Okay, cool. Now that is working. So next up, I would say we could write some tests to actually ensure that our compiler will work in the future as well. And the first thing that we can test right now is if the structure of our AST is correct. And so how will we do that? What I kind of thought of was we could just take the AST and like it's kind of hard to test the structure, like to replicate it and say, okay, this should be the structure, right? Because then we have to like every time we want to check something, we have to create a tree structure and have to like specify all the parameters of our expressions and stuff. So like if we wanted to just say, okay, this has to be a parenthesized expression, we would have to specify an expression, create a box, and full expression, for example, and we have to pass a binary expression, which would need an operator, left, right, and so on, and it would just get really messy. So what I thought would be a pretty good idea, I think, was to just say, okay, let's just flatten the AST. So we just take the tree and transform it to a flat list. So, for example, if we take this program, which we can just take a look at the first expression here, or statement. This is just a variable declaration statement, right? And a variable declaration statement consists of an obviously variable declaration statement. Then it has as a child the initializer expression. And the initializer expression in this example is a binary expression. And this binary expression also has like two children, in this case, a number literal expression. And the tree structure would look something like this. Maybe I can do some ASCII chart. AST. Variable decal. I guess can just do it like that. Initializer, yep. Something like that. Exactly. So that's how our HT looks right now for this first expression. Like we have a variable declaration and initializer, a number expression. And so flattened, it would look something like this. We just have a decal, then a binary expression, then a number, and a number again. And this is easily testable because we can just say, okay, here we have a declaration, binary expression, and then number. So let's do that. Actually, so written a little to do here. So I guess we could create a struct that does that for us, like I don't know, AST verifier. And what we'll need is like a, I don't know, test AST node. So we can just say, okay, I want a number. I want a binary. I want parentheses. Let statement. I don't know, variable. We'll probably need something like this. And our AC verifier has an like expected. It's just gonna be a vec of test AC node. And it probably will need input as well. I guess, yeah, probably just need an expected and make it actual. So pub fn new, and you will take input string and return self. Cool. And input and expected, which is going to be a vector of test AC node. So now what we have to do is we have to like compile the program, extract the AST, and then flatten this AST. The problem is that to create our AST, we have to create our parser and all the setup like diagnostic bag and stuff like that, which is already done in here, right? We already take an input text, create a diagnostics bag, create a parser, create an ST and stuff like that. And I suppose we want to kind of extract this logic to its own struct, so we can easily reuse it in our tests as well. And typically this is called a compilation unit. Compilation unit. And we can just put that as a module without a directory. Attach that. And essentially we just have a compilation unit struct which will hold an AST for now. And probably get diagnostics back. And yeah, that's it for now. So I would have a third compiler. And we can just take everything from main and put it in there. So guess probably everything up to here. Yep. Just put it there. Import everything. Blah, blah, blah. The check diagnostics method. Probably okay, cool. So I need a symbol checker, which is actually in here. Yeah, it was just weird code that we've written last time. We'll need to refactor that as well. I mean, that's fine for now. So now that we have this, we can say we'll return a compilation unit. I don't know what we'll do about this error checking here. I mean, we could map it to also return a compilation unit in both the error and okay case. I mean, that would actually be okay. Guess we could do that. Okay. Could do that. Just say okay, like map error, right? Yep, we could do that. So we just say map error. Don't care about the error. Can just say self create compilation unit. Something like this. And then we can just return a result which will hold compilation unit on success and a compilation unit error case. So we can do the same thing here. And you tell me that it's use a move value. Okay, that's actually not so cool. I mean, that's pretty weird, right? I think that's kind of a bug in Rust. Because does that make sense? Because this can only be called if this is an error, and then we'll leave this method anyway. Okay. Should probably not happen. Hmm. Okay. Mm, it's tough actually. Mm, maybe we'll just have to replace this with an if statement. Which is pretty ugly to be honest. I don't know if I want to do that. Hmm. I mean, okay, let's just do that. So we'll just say um, if it's error, we'll just create a compilation unit, and now we should not get any weird errors anymore, right? Expect compilation unit found. Okay. I don't know, is that like the way to do this? Because I don't like this, to be honest. Because what happens now is if you compile this, we don't even know if there were any errors or not. So that's not cool, right? Hmm. Yeah, let's just do it like this for now. It's not the greatest, but I mean it works for now. So what we can do here now is we can also move this logic. You can just say, okay, compilation unit, cool, you can compile it, and you can also run. And here we'll use the evaluator, and we'll say self AC visit. Cool, now that works. So we can say now is that compilation unit compile from the input, and we can just say compilation unit run. And I guess we don't even need that anymore. Can we clean this up? Nice. Okay, now we have a compilation unit, which we could use to create diagnostics. I don't know, testing. Okay. So what we can do now is we can say you want a new AST verifier. Okay, that's cool. So we first of all have to get an AST or let comp compilation unit compilation unit new file, and now we can flatten the AST. So we can say like, I don't know, flatten AST, which will just take in reference to AST, and we'll return you the back of test AST node. You can just say, okay, cool, that AST or like flatten is equal to self flatten AST, and which will take a reference to calculation unit AST. And we'll have to make this public, I guess. Help, please. Okay, cool. Now we can flatten our AST, and we can return AST verifier. Expected and actual. How will we do that? We will probably say like actual. Say that. Okay. Maybe we'll have to make this instance method. Yeah, I suppose. Like, because I want to implement this with a visitor, and we can only apply the visitor to an actual instance of our verifier. So we can say that verifier then we can return the verifier. So you'll see why I did that in a moment. So, because what we can do here now is we don't even have to return anything here. I will say self actual here. You need a reference here anyway. And then we'll say AST visit new reference to self. Exactly. And now we'll have to implement AST visitor for AST verifier. And in here we can just say, okay, we have a let statement. So we say self expect actual push AST let statement. Nice. The same thing here, same thing here, and we're not gonna do anything here. Do nothing, and visit parenthesize expression, and visit binary expression. Cool. So now we have basically flattened our AST. It's never used. Okay, because news never used. Okay, makes sense. Cool. And now we can actually implement a method, say like and verify, which takes a reference to self, and we'll just say, okay, we can assert, like we can go loop over the expected and actual. Yeah, we can do that. So we can say, how do you loop over? I mean, we want to loop over the longer list, right? We could loop over expected and just check if the node you're expecting node in actual matches, and then we can check if there are more nodes in actual than in expected. Yeah, yeah, that's fine. Okay, something like for. I mean, we could use zip. The problem with zip is that it doesn't like respect different size vectors. So we'll just take the shorter one. Yeah, no, let's do that. For index expected. Yeah, something like this. So let actual get. We don't want to unwrap you. I mean, we could say yeah, let's do it with zip. Let index expected actual in guess something like this. And here we can just assert a length match. So why do you not like me? Okay, because we have to use enumerate here. Yeah, okay, so we have to implement. Yeah, so our test AC node needs to implement some traits like debug and partial quality and equality. Cool, now that should probably work. So let's just write a simple test. So we can just say publif and should parse binary expression. Yeah, something like this. So with a let statement, variable in us are correct. We know what that. With a let statement number, binary number, number. So that should pass. It does not. Expected for no's, but got one. Okay, it's because we're doing the same issues that we always do because we always forget to visit stuff here. We have to actually visit the children, of course. Maybe worse now. Nope. But got one. Yeah. Okay. Wait, okay, because we do not visit our inlet as well. Now, okay, cool. That works. Now we have tests. Sure thing. Should parse. Like basic binary expression. Also extract this maybe. Search tree. I don't know. So GitHub Copilot, write some tests for us, please. I beg you. Now that's actually cool. And I think that might even be correct. Is it? Should parse parentheses binary expression with variable. Okay, we don't need to. Wait, why do you even work? Okay, that's weird because we have semicolons here. No, we just ignore, I guess. Parenthesize variable. B. You'll probably have a string here, so we can assert that it uses the correct variable. And we'll have to change that here as well. Cool. Now let's just run this whole test module. Nice one. Okay, so I'll get a Copilot. What other tests do you want us to write? Should parse parentheses binary expression with variable and number. Okay, so that's the last test in this pattern that we're gonna write. Okay, it's actually failing. That's interesting. That statement. So what's What's the error anyway? Expected 9 nodes but got 8. Last statement. Binary, parentheses, binary, what? We have a, wait, how does this AC even look like? So we have a binary expression with 3 and this thing, which then consists of another binary expression, right? So that's actually correct. So we have another binary expression in parentheses and binary expression, and then a variable b, which we have 3 binary expressions here. Am I missing something? I mean, okay, this binary expression is this plus, this binary expression is this asterisk, this binary expression is inside the parentheses, and so this goes to this, and this to this. I mean, this should be correct. Expecting. Okay. Maybe we'll also have to like print stuff here. Got 9 nodes. Actual nodes. So maybe that will help us. Actual nodes, let statement, binary. Oh, so we got less nodes. Okay, okay. So we have 1 node too much in here. Let statement, binary, parenthesis, binary. So we only have 2 binary expressions. I would say that's not correct. Just I think we found a bug, which is pretty cool. Yeah, we can also see that here, that our 3 is not parsed correctly because it is treated as a separate statement, which obviously is not quite correct. Okay, see that. So if we just paste this to our input string, like right here, that should not work either, right? Okay, we'll actually run into what? Oh. Okay, makes sense. We should not run this if there are errors. So maybe we should not make that public and just say, then maybe run. Yeah, exactly. We could call pilot and maybe run. So now we should not panic anymore. Cool. So it just says undeclared variable. I mean, why does this not work? I mean, sure thing, b is not declared, but that should not mess up our AST structure. So does this work when I say that b is equal to 1? No, it does not. Okay, that's actually interesting. So maybe we have to take a look at our parser here. Okay, so where is this happening? There's some issue probably in our parse binary expression method. I mean, I suppose it could be with precedence. Should not. So we're parsing a binary operator. After we parse our primary expression. So how should that work go out? I mean, okay. So if we take a look at this, we should first we should go into this method. Okay, we have to input it here as well. We should go into this method, and we should parse the first primary expression, which will be a parenthesized expression, right? This will be our first left hand. And this is parsed correctly, right? So if we say parse primary expression, we go into here and say, okay, we're left parenthesized expression, cool, fine. So after we have parsed this, we get into here and say, okay, cool, our current token is an asterisk, which has a operator, or is a binary operator, right? Because if we have an asterisk, we say, okay, cool, multiply. So we go into here and say, consume the token, and we get precedence, which is 2. And 2 is obviously not less than 0, which was passed in here. So we parse another binary expression, right? With 2 in here. So this will go into here as well and say, okay, cool. And parse a primary expression, which will be our b in this case, so a variable expression. Then we'll parse another binary operator, right? And this will be our plus, and our plus will have a precedence of 1, and 1 is less than 2, and so it stops here and doesn't actually respect the 3. That's not cool. I mean, what should happen is that we just parse this expression, and then we go into here and parse this binary operator. It's actually tough. I guess. I guess I'll have to think about that. Maybe I'll come back to that later. First we're gonna write tests for our diagnostics. So let's do that later. I mean, we have tests now, so we won't forget that something is not working correctly. It's a good thing. So we'll write tests here in here as well. So we'll say configuration test, and we're doing something very similar here. Like we're also just creating helper structs, like struct diagnostics verifier, which will hold once again actual diagnostics and expected diagnostic as well. So, I mean, same problem here. We want to make our lives a little easier, right? So, if we take a look at this, that's actually pretty hard to create yourselves, right? Because you'll have to create a text span, and text span holds a position in text. And so if we, for example, take a look at this input, I mean, that's fine, but let's say we have like 2 lines more input, you'd have to figure out at which position the error is that you want to mark, right? If you want to say, okay, this should mark an error here, then you'd have to count, okay, say 1, 2, you have to go to the start of the line, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Okay, and we don't want to do that, obviously. So what you can do to make your life a little easier is you can create kind of a another language inside your language. Basically, you can like mark the text spans where the diagnostics should be marked, or yeah, with like special characters, and then you can parse these and convert them into diagnostic structs. So you'll see what I mean in a bit. So we say like implementation of our diagnostics verifier. So what we're saying is new, right? We take input string and we'll say, okay, cool. We'll have parse input. What am I doing? Input string and import back diagnostics. So let's just write one example test of what I mean. So FN should report undeclared variable. Missing parentheses here. So we have an input like, yeah, like, I don't know, like let A equals B, and we want the diagnostic to be this B, right? So we can just say, I think I've copied this one. Yeah, we can just say buts. Okay, so now we mark the location where the error should occur. And we're using these weird little characters because we need something that has like an open and close variant. But we can't use like brackets because we will implement arrays later, which will use these brackets, and so that will destroy our tests. So we kind of think in the future. So we can say expected is, we need expected, like expected will just be an array of messages, right? Because we don't need to specify a text span and so on ourselves. And then we create a verifier, which expected is actually wrong because expected should, yep. So expected parse input. And actual. So this will also take our messages. I guess we can also rename this to messages. Now we can say like the expected is equal to self parse input, and actual is compile, right? So we just create compilation unit once again. And we'll clone those. These, I mean, that's fine. We'll cross the best, just tests, but we'll have to implement clone here. I'll copy that properly. I can implement copy for that as well. So we can say like that actuals equals self compile, which will take the input, and now we pass this. Cool. So now we just have to parse the input. So how will we do that? So we can loop over the entire text and like track the start positions of these. So anytime one of those occurs, we can just say, okay, here starts another span. And I think a pretty good structure for that would be like a stack, let mute, like start, index, stack, or something like this. Something like that. And we probably also need like a current position, maybe use size, because we can't just take the index of the child we currently add, because we have to like not account for these because they do not actually occur in the actual text that we'll also parse. And that's actually an issue because we can just compile this input directly. Say like if I'm like get raw text, because we have to like remove those. Like input or replace. Yep. Okay. So we can select like raw text parse input. Maybe we can just do that in our methods. So we have to say let raw text, and then we say raw. Yeah. So now our compilation should also work, and we can say same here like raw text self-get raw text. Cool. Yeah, and we'll have to keep track of diagnostics, I guess. So we can now loop over index, so in input.char, so enumerate. We can say like match C. Yep. So we push index, and else we just increment the current position. And it will return our diagnostics. So is that correct? They start index pop, yeah, nothing. Span, okay. Sense. And we can just say messages position. No, that's not right. That's not correct. Take the length of our diagnostics. And the message we'll actually need that here. Message. No, literal. Message. You can go here and like let literal. Yeah. String. Cool. I guess that could actually work. Eh, it did not. Okay. Byte index 10 is out of bounds. And index. Oh, cannot just say index, we have to say current position here. Cool, that works. Undeclared variable b. And that's also okay. We should actually also verify stuff. That would maybe make a little sense. So we first assert the length is equal. And then we can just say like for. Exactly. Thank you, good call. That's actually cool. Please work. Okay, you did. Expected literal. What we okay. What? Expected literal. So I guess that could be kind of not correct. push out because we're pushing the index here as well. Okay. Do we even need our index? I think we need the index. You can just say, take the char. So why do you not work? Expected literal. So, I mean, it gets to here, right? So start and then probably correct message as well. Literal is just not correct. So if we comment this out, it should work. Okay, cool. So why is the literal not correct? Current position. Why are we moving? We have to move from start index, of course. Cool. Now that works as well. And we have tests. So let's just add like one more test for like expected expression from plus. Like, does this actually work? No. Found. Okay. Something like this. Hash test and should report that token. And input is equal to let a equals like 8. And now we'll have to think of something really dumb. Like, no, that's not dumb. Like, yeah. Pretty bad character. I think we'll ever have that in our language, so it's fine. I don't even expected number. Maybe. Okay, what's the actual error message we got here? Should report bad token. Panic that byte index 11 is not HR boundary. Shit. So it's telling me that this weird little thing has more. Okay, it's not ASCII chart, I guess. So it does not have like 8 bytes. No, 8 bytes. Yeah, 8 bytes. 8 bits. 8 bits, not 8 bytes. But like more. Okay, that's actually funny. Hmm. 8. Huh. Byte index 11 is not a char boundary. It is inside. Okay. That's interesting. So we push the current position. Should be 10, right? Yeah, I don't know. Okay, maybe let's not use this one and then let's use a sketch art like, I don't know, let's just say we don't use this ad for now. Didn't work. Expected expression. Found that. Okay. Nice one. Do we have any other error messages right now that we can test? I don't think so, right? Report unexpected target, report expected expression, report undeclared variable. Okay. Nice. So now we have tests. And we can say cargo test. And we fail. Because we still have this one bug. Okay. And I guess we'll have to investigate this bug now. So this bug occurs somewhere around here. I mean, we already tracked it down as to why this would happen. Maybe this is just the wrong direction. I could, like, what happens if we just do something like this? I think that will break things even more, right? Yep. Okay, that's just not correct. I mean, let me think about that. So we parse a primary expression, right? I mean, we can just debug it. We can just say, okay, cool. We parse our binary expression, which will exactly result into another call parse primary expression, yeah, which should now be 1. Right? Yeah. Okay, cool. And now the operator precedence obviously higher than 0. Oh, let's see. Maybe we... No, we have to call this here. Because otherwise would not make any sense. I just thought maybe we could just say parse expression here. Because that would obviously be also allowed. But then we'll... like, this precedence will also always be 0, which does not make any sense. And this calls this method as well, so no, that doesn't make any sense. Okay, but I mean, that's correct. Operator is a plus now, right? Yep. So operator precedence will be 1. That's not correct. So we'll now parse another binary expression, which will be 3, I guess. Should at least be 3, 2. Wait, why is it 2? Oh no, it makes sense. Okay, 2, which should be 2. And now we will not parse a binary operator, right? So we should go here, right? Yeah, that makes sense. Now we're back here, and right is now our number expression 2. Okay, and we'll have a binary expression is now left. So next thing that we parse, we go back into here and say, okay, cool, are we a binary operator? And yes, we are. We're not. What? We're not a binary operator. Value 7. Okay, so we're at token 7, which is right parent. Huh. Okay, now that makes sense. Makes sense. Still correct. Now parse another expression. Because we're now back to here, right? Wait, are we? back to left part, not excuse me, it kind of makes sense. Because the stack just unwinded. Okay, cool. So now I've parsed the first primary expression. So now we're back here. Okay, now this is a parenthesized expression which shows a binary expression. Okay, cool. And now we have an operator. Multiply makes perfect sense. Now this right but should be yes, that's correct. And now our left should be variable expression. Why is our left a variable expression? What? Okay, that makes sense because that's correct up until now. And now our right should be variable expression. Okay, that's correct. Okay, so what's weird now is that I think it should work now because left is now a binary expression with an multiply operator, and now we should parse the next binary operator. But because of the precedence is even 0 here, right? So why does this not work? So which token are we at currently? Currently at token 11. What is 11? 11 is a number. 3. 11 is a number. Number what? So we've just... Well, one character ahead, right? We should be at 10. Because 10 is our plus. Why are we at 11? That's actually interesting. How can we be at 11? I mean, that would be an issue if we were at 11, because then we'll just not go into this loop. Right, we'll just skip over it, yep. And now we're done. Bop. Yep. Okay, so I think we found the bug. Now we have to figure out how to solve it. So the problem is that once we get to here, we're suddenly one token ahead, which should not happen. Okay, so I see the problem, because if we consume here and our operator precedence is lower, then we just jump out. But now we're one token ahead. So what we'll probably have to do is not consume until we're here. I think that should work. Yep. Very, very cool. Nice one. So, cargo test. Now all our tests are passing as well. So I think that's pretty cool. Now, next up, I think what I'd like to do is I'd like to implement some more operators, like just some more arithmetic stuff, like modulo, mod, and maybe bitwise ands, ors, XORs, something like that. Maybe even a power operator. Could be fun. Yep, we could do that. Yeah, and then I'll end the stream, and I think I'll stream later today again, and then we'll tackle if statements and scoping and stuff like that. So that will be interesting. So let's do that. So what do we want to work? We want, I mean, we could basically even write like tests for our evaluator. I don't know, let's not do that yet. Could write some tests, right? Tests and should parse bitwise and should parse bitwise or bitwise XOR bitwise not. Yeah, it's bitwise not. Okay, that's actually a little more complicated because this would mean we'd have to implement unary expressions, which we could do actually. I mean, why not? We could do that. It's unary. And shift, I mean, could also parse shift, right? Yeah, let's not do shift right now. Parse negation should parse power. Yeah, cool. And we can also probably verify like assert compilation unit, diagnostics bag, borrow diagnostics length is equals to 0. Probably also implement debug here. This. So this should still work. Cool. And our test should blatantly fail. Not found again. What's that? We could probably even convert to assert equals. So we would add like unary here. Cover tests. Okay, cool. Now we have to implement unary expressions. So let's do that. So we'll have to create new nodes here. Variable expression kind. Okay, so right beneath this unary, the unary expression. Right now, abstract AST unary expression. Operator token operand bar. Yeah. Okay. Cool. Do visit expression. Cool. And for our printer, literal and operate. Nice one. Verifier. Verifier will actually push unary and visit the operand as well. Okay, cool. Actually, do we want? How have we done the binary operator? Okay, I guess we'll like abstract AC unary operator. Yep. Enum AC unary operator kind plus and minus. Yeah, let's put plus for now. Let's just do minus. And AC unary operator, which will implement. Oh, we implement display for that one? No. Token, literal, span literal, okay. Fine, I guess. Okay, nice one. So we're still failing all our tests basically, which is fine. And because now we have to get into the actual parsing process. So, how will we parse unary expressions? What we can do is, like, actually instead of saying parse primary expression here, we can say parse unary expression. And like parse unary expression, which will return an expression that is t expression. Oh, kidding me, right? Come on. Yeah, that's correct. So if we have a unary operator, then we're gonna return a unary expression. Otherwise, we'll return a primary expression. So parse unary operator. So option AC unary operator. Kind. We do return a no, we don't return a kind here. That kind unary operator. Kind minus. Okay, cool. Unary expression new. Probably. Okay. Kind map. Sure. Fine. Constructor for this one, which will be called here. Nice one. Okay, now we'll have to add a constructor for our unary here, unary operator. Cool. It's being used here. And now we should be able to parse unary expressions, I guess. So maybe test will not fail. Okay, Stack Overflow. That's always great. Because why? Probably because we do not consume a token, right? Parse unary expression. So wait, what are you doing here? GitHub Copilot is so dumb sometimes. That's like unbelievable. Okay, maybe now. Stack Overflow. Still. Probably because we're not consuming our tokens here. So we probably have to consume here. Work, please. Thank you. Okay. So it should work now, something like this. Yeah. Nice one. So the tests that are failing probably related to, power, binary expression with variable and number. Okay, that's not cool. Why are you failing? Okay, probably because we're using an undeclared variable. Yeah, that's understandable. Should parse bitwise and should parse bitwise not. Okay, so we're gonna use add bitwise operators now. So something like this. To be honest, I don't really know the precedence of these operators. I don't know if they bind stronger than like a multiplication. I mean, we could try this out in Rust. We could just say let a, so 1 times 2, 3. 2. Does it make a difference anyway? No, it would not. Like, maybe this. So, if 2, maybe I could just ask ChatGPT maybe. Can you list the precedences of common binary operators? Cool. In order of highest to lowest precedence. Okay. So we'll have to add new binary operators here. Binary operator kind, which will be bitwise and, bitwise or, bitwise XOR. No, bitwise not is not a binary operator kind. Okay. Okay, cool. And probably even add power. Now we'll have to add precedence here. So what GPT said tells me is, so exponentiation, which is power, has the highest precedence. So we'll just get a precedence of 5. After that comes like multiplication and division. So we'll give that 4. Bitwise, then come like addition and subtraction. So you get 3. And then come like shift operators, which we don't have yet. And then come bitwise and bitwise or and bitwise XOR. So we probably even have to give this like a higher, let's just say 20. It doesn't really matter anyway. Get like 19. Minus 18. Bitwise and 17. Bitwise 16 and bitwise XOR. No, you get like 15 and you get like 16. So maybe we could even sort them. Okay, cool. Nice. So we now have to parse these, right? So we'll have to go into our parser and say parse binary operator, and so have to lex these first, I guess. We have to clean up here a bit. So we can say like, I don't know, operators plus minus square slash. I don't know, other this keywords. Yeah, then we can move this other stuff around. End of the enum declaration. We can say like literals. Okay, cool. And now what we parse is like ampersand. Ampersand? What? It's ampersand, right? pipe, and what's the other thing called? Caret, I think. Caret. Nice. Token kind. Also thinking, would it make sense to like have a power token kind? I guess like double asterisk. No. Double asterisk. I think it would make sense. Would make things a little easier on the parser side. I mean, that's also like pretty bad code here. I guess we could extract this rise macro, but it's fine. And I'll probably also refactor this into a match. Doesn't IntelliJ is IntelliJ able to do that? I don't think so. Yeah, it's unfortunate. So, consume punctuation. So what we are gonna do here is we'll say, okay, if ampersand your pipe caret, and we'll not direct, because the problem that we have right now is we can't just say that, okay, once we see an asterisk, we cannot say it's going to be asterisk tokens, could also be double asterisk. So yep, exactly. If next, okay, that's pretty ugly. We can do better, I hope. Can we? I mean, maybe. Okay, it's fine for now. I think about a better solution once we have to do this again, because that's just going to be duplicated code. Now, I think that should just work, to be honest. We'll probably have to add handling for these new operators in our evaluator. Could not compile. Okay. Not covered in visit binary expression. Exactly. Okay. So power is power. Okay. Okay. It is not parsed. Okay, why not? I mean, we've added these in the binary. Okay. Maybe we have not added the parsing yet. It's not and it's bitwise and bitwise or token kind double asterisk. Please. Okay, nice. Tests. 10 passed, 3 failed. Okay, so parse bitwise or not. Okay, we have not implemented that. That makes sense. Cool. Then let's also add our bitwise not. So we'll have to add another unary operator. Bitwise not. Bitwise not. So we'll have to parse this. Parse unary operator. Token kind tilde. Yeah. Bitwise not okay. So we'll have to add tilde here. tilde, and we'll consume this in our punctuation. Consume punctuation method, tilde. Okay, cool. So maybe that should work now as well. 11 passed, 2 failed. Cool stuff. And now these tests only fail because we have added the check that there should be no syntactical errors in our program. And the problem is that we use B here, even though B is not defined, right? Yeah, that's a problem. I mean, we could actually just fix this. B could 1, so we have to add another let statement here. And like number. I think that's fine. So pass now, right? Okay, cool. So we'll do the same thing here. Add like a let b equals 1. And hopefully all our tests will. So now our test. Nice one. Okay. So now we have passing tests. We have working stuff. Okay. I think that's not working. So right now, if we said something like minus b, we should probably get an error, right? Okay. Undeclared. Okay, makes sense. Let b equals 1. Not implemented. Yeah, makes sense. Unary operator guide. Bitwise not. That's not quite correct, is it? Wait, it is. Okay. Nice. Is this correct? Let's see. So, what binds stronger here? So the first thing that should be evaluated is this, right? So we say minus 3 times minus, no, 3 times minus 1 is minus 3, minus 3 and 3. Oh, Jesus. I don't like minus weight. Is that correct? It should be right. It's like minus 3. Yeah, I think that's correct actually. Because minus 3 is like that's all ones except for the last 2 places, which are 0. Yeah, and then when we end like 3, which is just 1 1, then these 2 ones are just discarded, and so we are left with all ones but for the last 2 places, which means that we are left with minus 3 again. Yeah, makes sense. Cool. And now what I want to try is if we can just stack these forever. Okay, we actually can. Okay, that's hilarious. Jesus. Yeah, maybe we should add a test for this. Like test and should parse hilarious amount of unary operators. Now like this. Like 6, 2, 3, 4, 5, 6. Okay, you're failing. Why? Expected binary. Okay, maybe we have. No, this should have been the correct one, right? Unity number 3. Wait, expected binary at index 1, but got unary. Okay, I think we hit another bug. Mm-hmm. Okay, let's see that. Wait, can I? Yeah, I think I can reproduce that. So, what do you think will happen when we type this? So, it should evaluate to 1, right? If I'm not mistaken, it will now evaluate to -3. Okay, yeah, it actually does. Okay, that's it's weird. It's actually weird. Let's see that in our parser. Parse. Oh, because we call it parse expression. Yeah, that should not be the case. We should call parse primary expression. And now we will evaluate to 1. Okay, it's fine. That's cool. And now we're failing this test. Still failing the test though. Oh, okay. So we should not call parse primary expression, but rather parse unary expression. Yep. And now all our tests are passed. Cool. 14 tests have passed. Bam. And that's correct. Okay. I mean, that's cool. I think we have done some nice stuff. Like we've added new operators. We have now support for like weird operators like this. I don't know, and plus tilde 9 should probably can compile. Yeah, okay, that's funny. And like we can lord this with a 98, and we can else can we do? Do we have any other operators? We have the power operator, like power to 2, yeah. Okay, so that's what we have done. What a mess. Okay, cool. I think that's it for this stream. We've added tests for our diagnostics. We have added tests for our AST structure. And yeah, I think I'll see you later. And then we'll add like control flow structures like if, else, while, maybe even a for loop. I don't think we'll do that just yet. But yeah, see ya.